Hello and welcome to the lecture on selection sort. The selection sort algorithm sorts an array by finding the smallest item repeatedly and placing it at the beginning of the unsorted partition. To illustrate this process, let's dive into an example. Suppose we are given this array. As is observed, the array is unsorted. So initially, all elements are within an unsorted partition, distinguished by a red color. The algorithm operates on the principle of discovering the smallest element in the unsorted partition during each iteration and positioning it correctly within a sorted partition. Now, let's walk through the steps of selection sort, breaking down the process step by step. The length of the array is 6, and the loop starts from 0. Firstly, we define a variable for storing the index of the assumed minimum value, which is the first element of the unsorted partition. We select the first element from the unsorted partition. This selected element is assumed to be the minimum for the moment. Then the algorithm iterates through the rest of the unsorted portion, comparing each element with the initially selected minimum. If the algorithm finds an element that is smaller than the assumed minimum, it updates the minimum to be the newly found smaller element. After completing the iteration, the algorithm swaps the initially selected minimum with the actual minimum found during the iteration. This is a very simple and straightforward intuition behind selection sort. If it is confusing, then I promise it will get easier after watching this video. Let's move on. Go to the next line, and as you can see, j starts from i+1. It starts from a different index number because we want to compare the remaining elements with the initially selected element as the minimum. Accordingly, go to the following line. Now check whether or not the second item is less than the first item we selected as the minimum. 25 is not less than 6. Go ahead and increment j to compare the next item with the assumed element as the minimum. Now we must check if 34 is less than 6. Again, the condition is not true. Move on and increment j to check whether or not 14 is less than 6. The condition is not true. Increment j and check whether or not 50 is less than 6. The condition is false. Move on to the next element. This is the last element that we will check in the first iteration. Go to the next line and check whether 4 is less than 6. The condition is true. Finally, we found the smallest item in the first iteration. Go to the next line and update the previously selected minimum to the newly found minimum, because this is the actual minimum. Now proceed to the next step by swapping the value 4 with 6 to position 4 at index 0. We must swap the newly found item with the first element of the unsorted partition. Please note that despite our first assumed minimum element was the element with the value of 6, it was also the first element of the unsorted partition. In addition to the unsorted partition, there is also a sorted partition where 4 is one of its members. Go to the first loop and increment I for the second iteration, and then update the value of the minimum index variable, which we'll refer to as min-index here. Now we must start with the first element of the unsorted partition. We always must assign the index of the first item of the unsorted partition to a variable which is explicitly defined for holding the position of the assumed minimum. Go to the next line and update j. As you can see, it's 2. Now go to the following line and check whether 34 is less than 25. The condition is not true. Move on and increment j and then go to the next line to check whether or not 14 is less than 25. The condition is true, therefore update the minimum and assign the index of 14 to the min-index variable. Please note that in each iteration, all elements are examined against the current minimum value to find a possible actual minimum value. Therefore, in this iteration, we still need to move on with the remaining elements to find a potentially smaller element. Go to the next line to check if 50 is less than 14. The condition is not true. Increment j and check whether or not 6 is less than 14. The condition is true and a new minimum is found. In the next line, update the minimum index variable to the newly found index. Swap the element with the value of 6 with the first element of the unsorted partition. Go ahead and increment I, and then update the value of the minimum index variable and j, respectively. In the next line, check whether 14 is less than 34. The condition is true. Go to the next line to update the value of minimum index variable because a smaller element is found. Move on and increment j. Go to the next line and check whether or not 50 is less than 14. The condition is not true. Increment j again and go to the next line to check whether or not 25 is less than 14. The condition is not true, and then go to the following line and swap 14 with 34. Since no smaller item was found, therefore the assumed minimum value has taken into consideration as the actual minimum value. Therefore swap 14 with the first element of the unsorted partition. Please note that we effectively expand the sorted partition by one element and reduce the unsorted partition by one element. Do the same process and increment I, min index, and j respectively. Select the first element of the unsorted partition as the assumed minimum value and check if 50 is less than 34. The condition is not true. Move on and increment j to check if the next element is smaller than 34. 25 is less than 34. Therefore, a smaller item is found. Go to the next line and update min index, and then go to the following line to swap the newly found element with the first element of the unsorted partition. Go ahead and increment I, and then update the value of the minimum index variable and j, respectively. In the next line, check if 34 is less than 50. The condition is true. Go to the next line to update the value of minimum index variable, because a smaller element is found. Then go to the following line to swap 34 with the first element of the unsorted partition, that is the element with a value of 50. Move on to the last step to accomplish the last iteration. Update the value of I and minimum index variable, respectively. However, further progress is not possible regarding the inner loop. When the lower bound becomes equal to the upper bound, it signifies that there are no remaining unsorted elements to explore. Here the lower bound is equal to I plus 1 and I plus 1 is equal to 6, matching the length of the array. Therefore, no unsorted elements remain to explore. Consequently, the process cannot continue. Go to the next line, and as is observed, ARR of I is equal to ARR of min index. So the last item is in its correct position, and we can put it into the sorted partition. Now the given array is sorted. Thanks for watching this video, and I hope you enjoyed learning.